Hey, what's going on, guys? Kinsey here. In this video we're going to be running test programs for our 8-bit breadboard computer emulator built by Banner originally. So here I have a project by J Chandra 86, who has created yet another Banner's emulator, Banner's computer emulator, and he has provided some test programs that we're going to be relying on in order to test our emulator. And the good news here is that it does have both the binary that we're supposed to be reading from the hard drive and executing later on, like initializing the RAM from them and executing. And also it has this assembly files, which gives us mnemonics to get an idea of what the program is supposed to be doing and how exactly. So hopefully this is going to be useful. We'll later, I believe we'll later write our own assembler and disassembler as well. And yeah, probably not that sophisticated like the one available here, because I think that two-step assembling is an overkill if you have only 16 bytes of memory, and it's more educational, more didactic to set up the addressing manually, because if you do use the labels, you might not really be having that understanding of what exactly is going on there. So yeah, but it's a little bit off topic. So I actually do have these files being downloaded here, and now we're going to be using them. And also this project as the default program that comes along with the emulator itself is the program to print the triangular numbers. And here is the program, and I've manually disassembled this, and now it's available in our code here. So this is what the program does. I think we're not going to be going for this code because I'm planning to make some separate videos, like Banner's assembly crash course of some sort, just to focus completely on how to code in this, I believe, simplest possible assembly. But for now, we just want to run the program, and without diving into the details, like what exactly it does, we just need to make sure that the output is going to be exactly the same like we have here in this already existing emulator. So without further ado, let's actually try to run the code, and here we go. So we got exactly the same output. So now we just loads the RAM with this kind of values. So here are the mnemonics in the commentaries. So what it does, it loads to the A register the value available at F. So this data, so literally this is going to be, so after this line is executed, A register has 0. Then we add into whatever we have in the A register the value that we have at the address 0E, this here. And here we have 1, so after this line, A register is going to be equal to 1. Jump carry to 0x09. Here's literally just some cleanups. So we go there if we go above the 255 for FF in hexadecimal. So otherwise, we just output whatever we have in the A register. Then we store in the value of the A register to the F, the very last memory cell. And then we again load in whatever we have in E, and then add in whatever we have in D. And then we jump in back to the very beginning of the program. So just to give an idea that the program actually does something here, and does rely on all those instructions that we have implemented. And quite surprisingly, I didn't even change anything since the last video, so it seems like it's working more or less properly. Okay, so just to give you an idea, the output is exactly the same as we have here, right? So yeah, hopefully it makes sense. But how can we run those programs that already are kind of already written for this sort of a thing? So we can use this binary things here. So the very first thing to consider, I just want to import a couple of packages. So I want to say import sys to be able to use the command line arguments, and also I want to import time, because Banner's computer actually load to manually adjust the clock speed. So doesn't really make that much sense doing here, but I think that might be the case basically. Okay, so now let's refactor the code a little bit. So in the run, I want to load the program. So I don't want this one. Actually, yeah, I don't. So here in the run, I want to say init CPU, and here we go. Then load program, CPU load. Yeah, I also need to think like how to where to specify the file name. So probably here, and the speed as well. So let's say file name and speed. Okay, so here the file name, let's just drop it for now, and the speed, let's make it 0.05 for instance. What am I trying to do now? I actually want to so first of all, I want to here I want to add the clock delay. So time.slip, and I want to convert to the float whatever we have, the speed basically. So we're going to be specifying the speed as the command line argument. So here let's make it like 0.5. So it's, for now I just make it string, but later on it would be taken from sysarg system command line argument, so it's going to be the type of string. And I'm also thinking about the file name. So here let's say yeah, let's just add the file name here like this, and then in the load, so here if file name, so if file name is equal to nothing, to empty string, in this case we want to load the default program. Let's say print no file specified running triangular numbers program by default. So this should be the case, and yeah. Okay, let's try to run, and here we go. So no file specified, hence we're running the triangle numbers program by default. And now we also have this delay being added, so it sort of mimics the clock, like slowing down the clock delay. So the clock cycles is not that kind of fast as, well, obviously on my laptop it's just light and fast, and on original Benitor's computer it's around 300 hertz if I'm not mistaken, so somewhere around like that. Okay, so far so good. So now we want to computer run. So let's just print file name and sys argv1 and speed sys argv2. And now probably gives an error. Okay, list index out of range, which is correct. So now let's say file.bin and 005. Yeah, now it does. So we have the file name and we have the speed. Okay, so let's make it try accept. So we have the file name is equal to, yeah, like this, and speed by default is equal to 0.05. So let's make it just default then. Okay, maybe even we could split those. Well, I'm not sure. So we could specify them in separate. Yeah, it's not the most ever. Can I make it like this? File name. Okay. Okay, now if yeah, it doesn't print anything. Yeah, it's okay. It's okay. So here we have file name equals to argv1. Here speed argv2. Here I want to print let's make it here. So print say extras. Okay, so print file name and the file name, and running it, and then speed and milliseconds. File name none, running at milliseconds. Okay, so just a little hack. So no file specified. Okay, running at, okay. Yeah, this should be just okay. And if I specify some file name, it's not gonna be working, but yeah, file name. Okay, yeah, so this, I think this should be just okay. All right, so now the most essential thing is how actually do we extract the bytes, the data from the binary file? That's the most essential thing. So here we want to read data from binary file, and just say else and print, let's say, reading from and file name. We're not going to be using this later on, but for now, yeah. So reading from FFFF. That's okay. Now now the next thing. So we need another try except. Yeah. For now, let's say just with open file name, and we want to read bytes as F, for instance, and let's create the program equals to f.read, and let's print the program. Okay, so now it just gives an error because we don't have such file or directory. So here, let's add another try except, and let's say file not found here, and the file name. And also here want to say sys.exit and error. Okay. But in the case if we do have the file, so for instance, we go for programs, and which one to take? Let's take this add.bin. Okay, so still didn't find programs. Well, what am I doing wrong? I'm sorry guys, I just want to see if this is the matter of file not found or what exactly. So this, yeah, file, no such file or directory. No, hold on a sec. What? Oh, whoa, yeah, okay, that's because of this. So here, file name, and here the speed, and so you want to extract file name and speed from command line arguments, and here want to run computer, and all this I want to say if name is equal to main. Only in this case we stop here. So this is needed in order to if say we want to use this class somewhere in the third-party code, in this case it's not going to be initializing and running in that case. So run only directly, only if invoked directly. Okay, let's go. Okay, and here we go. So we just read the bytes, but it's not something that we can use kind of straight ahead. So instead, well, probably one of the simplest way possible of doing this is to use a list comprehension. So let me find let's say I for I in here, and I want to convert it to hex. And yeah, now it's much better. So now we have integer. Well, actually, hold on a sec. These are strings. These are not integers. So yeah, I'm sorry. We just want to make them integers. Yeah, and if I want to print them, I can say print. Here I can print hex for I in program. Yeah, so now it prints as strings, but literally these are the integers already. So now we can do actually use these guys to initialize our RAM. So also another thing that we need to care about is the length. So let's say print program length and the len of program. So it should be 16. So yeah, there is another limitation introduced here. So all the programs should be exactly 16 bytes long. If we don't use something, we just put in the no operations there, nopes. So let's say if the len of the program is not equal to 16, then we want to print program length should be exactly 16 bytes, and let's make it an error, and sys.exit. Yeah, but it doesn't because it has exactly 16 bytes length. Okay, and now so here we want to check program length. Here want to read program bytes. And now the next thing, we want to initialize RAM with program bytes. So how are we going to be doing this? So let's say for I in range and the length of the RAM, which is 16, self.ram. So here self.ram indexed by I is equal to program indexed by I. That should do the trick. And like this. And also here I want to print debug, so self.debug, and oh, internet failed. Okay, we're back. Self-debug, and then sys.exit, and because I just want to make sure, before running the program, I just want to make sure that it is in the random access memory. So yeah, so we got this, 51 4E. Yeah, so we just initialized our RAM from the program taken from here. So now, in theory, it should be running the should be printing the Fibonacci sequence. If I did everything properly, in that case, it should be printing the Fibonacci sequence. Okay, and also it's time to put this go back within the try except and paste. All right. And I hold my breath, and now we're going to be running this Fibonacci. So this kind of program is gonna be running now. Let's have a look. And yeah, it really looks like and feels like Fibonacci sequence. So far so good. Okay, so let's try then this add ASM. So what it does, LDA 8, so 0, 1, 2, 3, 4, 5, 6, 7, 8. So 7 goes into the A register, and add in whatever we have in the 9. So it's 7 plus 3 is going to be equal to 10. Then just subtract whatever we have in 10, subtract 2. And this should be 8. So this program should output the value of 8, if I understand something in here, out. And 0 is just because we don't use literally any arguments. So this program should output 8. Let's see if it does so. So add.bin, and indeed we have 8. So far so good, fantastic. Okay, now let's have a look at multiply, for instance. So this is gonna be more interesting. Perform a multiplication function by looping through the range defined by the factors. Okay, the loop ends when the subtraction of the first factor by the loop counter reaches -1. Well, I'm not sure whether this is gonna be working, because the way how this particular implementation is done is a little bit different. So it does seem to rely on the sign integers. Well, Beneder's computer doesn't seem to be relying on those. So I'm not even sure if this custom example is going to be working. But yeah, I don't know what's the output. Should be, well, we can run the original code to figure out, but yeah, let's just try to run and see if it works or not. Whoa, program length should be exactly, so it's not even 16 bytes. Well, okay, no matter how, I'm not sure how much bytes is there. Maybe let's say if it's more, should be no more than 16 bytes. Mul bin not found. What do you mean not found? Oh, it might just be, hold on, it just might be given into the error of some sort. Yeah, just hold on a sec. It might be running into a sort of an error, list index out of range. So what's the length of the program? Well, anyway, this, 15. Okay guys, just hold on a second, I need to figure out what's wrong here. Okay, so just managed to run it. Yeah, actually we need to loop over the range of the program, not of the RAM. So here I changed from self.ram, from self.ram, I changed to the line of the program. Right, yeah, everything else is fairly the same. Yeah, and it even does give an output of 42. Yeah, I want to print the program. Just trying to figure out what values it's trying to multiply. It would be nice if it prints the values it's about to be multiplying. But yeah, I think that, yes, 6 multiplied by 7, I think this is the case. So 6 multiplied by 7 is indeed 42. So yeah, quite a fun. Even this program kind of works. That's cool. Okay, so we got the multiplication working, and the last but not least is the count. I'm not sure what exactly it's doing, so probably loading immediate data 0 to A register output, then increments by 3, and if it goes to carry flag, so if it's greater than FF, then it's just, yeah, so probably just should be printing the values with the increment of 3 from 0 to FF or 255, and then goes back, something like that. That's what I can say by inspecting the source code. So let's try this count.bin. Okay, and indeed, yeah, indeed we do count. Yes, indeed, we do count from like increment 3 here. So it goes to 255, and then I believe then it should be counting back. It should be counting back after, and indeed it does. Yeah, so we were here at 255, yeah, 252, and then we're going down. Yeah, so this is fantastic. This is really awesome, I believe. This is really fantastic. Okay, and yeah, probably also, yeah, it just goes like in never-ending mode. I'm not sure whether this should be the case. Let's have a look at the source code. Print down, so output. Yeah, on the case of when it reaches the 0 flag is there, it actually jumps to up. Yeah, so it is intended to be, it seems to be intended to be running in a never-ending mode. So far so good. So yeah, I think this is good enough proof of example proving the concept. So I think these examples are enough to prove the fact that the emulator, the Banner's 8-bit breadboard computer emulator, seems to be working quite okay, quite nicely. Yeah, still, it's yeah, I don't see like the tests for wrapping around. I mean, like if it goes above 255 and if it goes below, it just relies on the carry flag and the 0 flag, but the values at the A register might not be handled that properly. So these examples are unfortunately not covering that, and the code, the original code where I taken these examples from. So this code, it's not really clear. It's like if you have a look at the implementation here, you see like for subtraction, he just does self A minus self B, and it doesn't. So this would result in a negative number if this would be a signed number. So I don't see that it makes them unsigned somewhere. So to make it unsigned, you actually need to bitwise end with a FF. All right. So what else? Maybe one last thing here to consider is, yeah, if we just run it like this, name speed is not defined. This is interesting. Oh, that's because your speed. Okay. Yeah, and probably we can just add the usage here. So print usage in Python 3 breadboard dot py programs, let's say Fibonacci.bin and 0.05, for instance, like this. Yeah, okay. And I just want to print this only if there is no file name. But on the other hand, let's say if, or maybe, yeah, maybe put it here. Maybe here. Yeah, so now it's okay. And if we do, let's say the Fibonacci, I just want to make sure that this example should be working out of the box. Copy. Paste. And it does. Okay, so far so good. So yeah, guys, this is it from my side in regards to this part, and the next couple of videos, I'm not sure, maybe I just make it in a single video. Probably it makes sense just to make it in a single one, even though it would be a bit long, but who cares. Yeah, so assembler and disassembler. So I'm gonna be I want to write the assembler that would allow us to print the code, to type the code for Benny's computer in this sort of way. I'm not going to be using labels because it's an overkill for 16 bytes. So this two-step assembling is definitely not on the cards at this particular situation. This we can cover it later on for 6502, for instance, or whatever else. But sorry, but for this one, I don't see any sense in doing so. And another reason, like. This Benny's assembler is fantastic to be the very first one to start working with, basically. And when you're just starting learning assembly, especially the simple one like this, it's really better to not use these labels, because you just don't have a proper understanding of what's going on under the hood. So I emphasize the need of doing everything manually to get the understanding, because otherwise there is no other sense to do this other than for understanding, for gaining the proper understanding, because you're not probably going to be writing code in assembly in your daily job, right? But for learning purposes, it might be making perfect sense. So yeah, assembler and disassembler hopefully coming in the next video. This is it from my side. Thanks for watching. Until the next time, and take care.